Hello everyone, welcome to this lecture. In the previous lecture we studied FRF measurement using an impact hammer. In this and the next couple of lectures we are going to look at how FRFs are measured or how FRFs can be measured using a shaker. And in this particular lecture we are going to focus our attention on excitation of a structure using shaker. So, the topic today is as you can see, excitation using a shaker. So, a brief outline of the lecture is as follows. First we will look at a typical experimental setup for FRF measurement using a vibration shaker. Then we will look at the basic construction of an electromagnetic or electrodynamic vibration shaker, and then we will look at how the shaker is attached to the structure. After that we will look at shaker structure interaction, and we will use a lump parameter model of the shaker structure system in order to see the interaction between the two. We will also look at what quantities should be measured, what signals should be measured in order to estimate the FRF of the structure. And then at the end we will look at in brief what is a piezoelectric force transducer and an impedance hat. So we have seen excitation of a structure using impact hammer. So are there any limitations of excitation using an impact hammer? One of the limitation is that the hammer may not be suitable for exciting large and heavy structures. The large and heavy structures would require much more amount of energy to be imparted to them in order to vibrate them. And then because with the impact hammer the force is applied in the form of an impulse, and therefore if we want to impart a large amount of energy, then the amount of force that needs to be applied will be very high. And then applying a high amplitude force may cause local damage to the structure, right, wherever the impact is made. In addition, a larger amount of force may also excite any nonlinearities that might be there in the structure. And since in model analysis our interest lies in measuring FRF corresponding to a linear approximation of the structure, the purpose of measuring such an FRF would be defeated if the nonlinearities are excited. So this is one of the problems with impact hammer when larger amount of vibration energy is to be imparted. The other limitation is related with the fact that the excitation frequency range cannot be precisely controlled, right. With the impact hammer the frequency range that is excited, it depends on the contact stiffness between the hammer and the structure, right, and also the inertia properties of the hammer and the structure. The frequency range with hammer can be changed by using a different hammer tip like a rubber tip or plastic tip or a metal tip. However, if we want to have a specific frequency range which we want to excite, then that control is not possible. So these are the two of the limitations of impact hammer. What about excitation using a shaker, a vibration shaker? These limitations can be addressed by using a shaker for excitation. So it can be used for exciting large and heavy structures, right, because here we are going to use continuous excitation rather than an excitation in the form of an impact, and therefore the larger amount of energy can be imparted to the structure with continuous excitation. Also the excitation frequency range depends on kind of excitation signal that is used to drive the vibration shaker. And as we will see, we will use basically a signal generator to generate a signal of specific type and with certain frequency domain characteristics, and by choosing the signal properly we can tailor the frequency range of excitation. So this is another important advantage of using a shaker. Let us now look at briefly the experimental setup for FRF measurement using a shaker. So this is a typical setup that can be used for measurement of FRF using a vibration shaker. So here we are testing a structure under free condition like this car body structure. So we see that it has been suspended by soft elastic bands, so that the free boundary conditions could be simulated. So and then this is, you can see this is the vibration shaker, right, which is there. So this vibration shaker would generate an alternating force, right, along its axis of vibration. So in this case it is going to generate an alternating force in this direction. okay, it is going to generate a force in this direction. This force is then transferred to the structure through a stinger, what has been shown, and then in order to measure the force that is being applied, a force transducer is used. So, you can see that this is the force transducer which is there. Now the shaker is driven by a signal generator, right. So, you can see this is the signal generator, and then any specific signal of desired frequency range and properties can be generated, and then this is used in order to drive the shaker. The output of the signal generator is a low power signal. So, here the output is a low power signal. So, signal generator output is a low power signal, and that cannot be used to directly drive the shaker, because shaker has to excite the structure, right. So, it requires larger amount of energy for excitation. So, therefore, power amplification is required, and for that purpose the power amplifier is used. Power amplifier generates a signal which is having a larger amount of power, right, but has the same frequency characteristics as that of the signal it receives from the signal generator. So, in this way the shaker generates a force signal which is having the frequency domain characteristics as dictated by the signal generated by the signal generator. So, then when the structure is excited, now the vibration response of the structure is measured. In this case, you can see an accelerometer has been used. So, this is the accelerometer, right, that has been used, and then the output of the accelerometer and the output of the force transducer, they are then fed to the FFT analyzer. Now, these outputs of these transducers may have to be conditioned, right. So, we may require some signal conditioning in between the FFT analyzer and the transducers, and the kind of conditioning required, whether it is required or not required, and what kind of conditioning is required, that depends upon the type of these transducers. So, there are three possibilities. If we have, let us say, charge types of sensors, right, charge types of these transducers, the accelerometer and the force transducer, if they are of charge type, okay, if they are of charge type, then we require signal conditioners in the form of charge amplifiers, right, then we require charge amplifier in order to convert the charge signal into voltage signal, and then they are then fed to the FFT analyzer. The second possibility is that these transducers, they are of IEP or ICP type, as we discussed in one of the previous lectures, right. So, if they are of IEPE or ICP type, right, and the FFT analyzer also has its input ends which are compatible with such types of transducers, right. That is, the FFT analyzer must have the ICP compatible ends, so that the necessary electric power required for the functioning of these transducers can be supplied, that CCLD input, enabled inputs are required. So, in that case, then we do not require any signal conditioning in between, right. Directly the output of the such transducers can be directly fed to the FFT analyzer. So, IP and compatible FFT input ends. If that is the case, then no signal conditioning in between is required, no signal conditioner in between transducers and FFT analyzer, right, is required. The third case is where the transducers are of IEP or ICP type, however, the FFT analyzer does not have ICP compatible input ends. For example, some other data acquisition system is used which may not have this these compatible input ends. So, in those cases, then we require a signal conditioner in between the transducers and the data acquisition system, and those signal conditioners essentially would supply the necessary electric power for the operation of these transducers, and then the output of those signal conditioners basically will be the voltage signals, which would be then fed to the data acquisition system or the FFT analyzer, as the case may be, right. So, if we have IEPE or ICP types of transducers and the FFT or DAQ system does not have compatible input ends, right. So, if that is the case, then signal conditioner is required. Okay. So, we require signal conditioning for each of the outputs of these two transducers. So, once these signals are required in the FFT, the FRF can be estimated, right, as we have studied earlier. So, there are several applications in which a vibration shaker is used in practice. One of such application is vibration acceptance testing. So, we see that there are several products or systems which operate in an environment in which they are subjected to severe dynamic loads or vibratory loads. For example, a satellite structure, when it is launched, it is subjected to very severe dynamic loading. Similarly, the electrical and electronic instruments on board ground and aerial vehicles, they are again subjected to vibratory loads in their service life. So, it is necessary to check whether such systems can they sustain the vibratory load in practice or not before they are put into service. So, for this purpose, vibration shaker can be used. So, vibration shaker is used to simulate the same vibratory environment in laboratory which these systems are expected to experience in their service life. So, therefore, a certain vibration level in terms of several levels of excitation like 2G, 3G or the kind of level which they are supposed to be exposed to, or that vibration is generated in the laboratory, and then it is tested whether these structures or systems can they sustain these vibrations without failure. Okay. So, therefore, this is an important application of vibration shakers. And because the vibration levels which are to be generated, they are to be of specific magnitude, a vibration controller is also used along with vibration shaker. Okay. Basically vibration controller is based on feedback control, and it ensures that the vibration level generated by the vibration shaker is equal to the level which that system is going to experience in the service life. Another application of vibration shaker is in model testing, and which is something we are going to talk about, right. In model testing, our objective is to identify the dynamic characteristics of the system, and for that we apply an input and we measure the input, and then the output that is resulted, that also we measure, and from this information about the input and output we try to figure out the dynamic characteristics of the system. So, therefore, in this application it is not necessary to apply specific amplitude of the force or any specific vibration level we would like to realize, right. The level should be good enough so that the signal to noise ratio is high and we can take good measurements or accurate measurements. That is only the requirement. So, therefore, here vibration control is not required with a vibration shaker. The other application is in material properties identification and also for fatigue life assessment. So, these are two other applications where vibration shaker can be used. So, there are several types of shakers that are available, like we have mechanical, then hydraulic, electromagnetic or electrodynamic, and piezoelectric. So, these are the four types of shakers that are available. We will focus our attention on electromagnetic or electrodynamic shaker. So, let us look at now the basic principle of working of an electrodynamic or electromagnetic shaker. The basic principle of an electromagnetic shaker is that when a current carrying conductor is placed in a magnetic field, then it experiences a force called Lorentz force, and it is seen that the frequency of this force is same as the frequency of the current which is passing through the coil. And if we want to generate an alternating force as we want in model testing, for generation of vibration, then we need to pass a alternating current through the coil, and by controlling the frequency of the current we can control the frequency of the force that is being generated. Okay. So, this is basically the principle of working of an electromagnetic shaker, right. So, let us now look at the basic construction of an electromagnetic shaker. So, this is the basic schematic arrangement of an electrodynamic or electromagnetic shaker. So, here we have this coil, we can see this armature coil here, right. This is the armature coil. So, this coil wound around a spider, right, and then on the top of the spider there is table, Okay. So, this table and spider together with the coil, it forms the complete armature. Then this armature needs to be supported, it cannot be it cannot hang in space. So, it needs to be supported, and that is why we have something called suspension, right. So, this suspension is very flexible and then it supports the armature over the on the shaker body. So, this is the shaker body, you can see. Then we need the magnetic field. So, you can see here we have a permanent magnet used here. We have used a permanent magnet here, and this is the NS poles of the magnet. So, this is the magnet here. So, in small shakers permanent magnets are generally used, but in bigger shakers which are meant for generating larger amount of forces, an electromagnet is basically used to generate the magnetic field. Now, this magnet will generate magnetic field with magnetic lines of forces starting from pole, the north pole and terminating at the south pole. Now, here in the shaker two pole pieces of soft iron are used as shown here. You can see this is inner pole piece which is at the top, and then we have the outer pole piece like this. So, this is the inner pole piece here, right, and then we have, you can see this is the outer pole piece, right. So, the purpose of these two pole pieces is to direct and concentrate the magnetic lines of forces into a small gap. So, you can see there is a small gap between the the inner pole piece and outer pole piece. So, these pole pieces, they are made of soft iron, and soft iron has much higher permeability than air, right, because if these pole pieces are not there, then air would be there through which the magnetic lines of forces would pass, but air does not have as high permeability. So, these pole pieces help to increase the flux density and reduce leakage. So, now we can see that between these two pole pieces we have the armature coil, and therefore, the magnetic lines of forces going from the say inner pole piece to the outer pole piece, they are intersected, right, they are intersected by the they are cut by the coil, right, armature coil, okay, and then therefore, that gives rise to a force on the coil that we will see on the next slide. Then this shaker body can also be turned along the axis of turning. So, you can see we have this axis of turning here. So, this is the axis here. So, this shaker body can be turned along this axis so that it can be oriented at the desired angle in the vertical plane. This enables to apply the force at a particular angle on the structure, okay. And then of course, this is the shaker base, right, on which the whole shaker body rests. So, this is the construction of the electrodynamic shaker. So, how now this force is generated? So, let us look at this figure now. So, this on figure A we have shown basically the front view and top view of the armature with the coil, and only a small dl length of the armature coil has been shown, right. So, we see that in the lower part of the figure, this is the dl length of the coil, right, which is wound around the armature. So, this is the armature, right, and so this is the armature and this is the small dl length of the coil, and then since the current is passing through the coil, this is the current vector, and then the magnetic field, it intersects the coil. So, the B is the magnetic field vector, and we can see that the magnetic field vector is perpendicular to the current vector, right. In the B part of figure, this is clear that we have this current element here, IDL is the current element vector, right, and then we have this magnetic field vector B, they are perpendicular. So, the force produced on the coil is given by the cross product between the current element IDL and a magnetic field vector, right, and therefore, the dF will be perpendicular to the magnetic field vector and the current element vector, and that is why you can see dF is now perpendicular, it is in the vertical direction, okay. And if we integrate this force on this current element over the whole length of the coil, we will get the total force acting on the coil. So, that is nothing but the force F is equal to BIL newtons. So, this is in newtons. So, this force F acts on the armature in the vertical direction like this. So, this is the force F that would basically be generated on the armature, and then this armature along with the coil will vibrate in the vertical direction under the action of this force, right. So, this is how force is generated by an electrodynamic shaker, and it depends on the magnetic field strength, the current passing through the coil and the length of the coil. Now, another important consideration is that how the shaker is attached to the structure. So, one way we can attach the shaker to the structure is that we directly attach the shaker table to the force transducer, right. But then in this manner the movement of the structure will be constrained by the structure, by the shaker, okay. And therefore, basically it will change the boundary conditions at the point of attachment. So, in addition to applying the force at the point of attachment, it will also, the shaker will also offer resistance to the motion of the structure in the direction of motion in the other degrees of freedom, right, and then the boundary conditions will be altered and the dynamic characteristics of the structure also will get altered. So, this is something undesirable. So, what we need, ideally we want that the force should be applied only along the degrees of freedom which we want to excite. So, if there is a certain degree of freedom at a certain location we want to excite, only along that degree of freedom the force should be applied by the shaker. That is something what we want, right. And how this can be achieved. So, what is generally done is to use what is called as a stinger, right. So, you can see here it is shown, this is stinger, okay. So, this stinger is basically a thin rod which is quite stiff in the axial direction, okay, but it is flexible in the transverse direction. So, this stinger is stiff in this direction, this is axially stiff. So, because of that it can transmit the force exerted by the shaker faithfully, right. It can very faithfully transmit or transfer the force from the shaker to the structure, right, because it is rigid in that direction, it is very stiff in that direction. But at the same time it is desired that the motion of the structure in the other direction should not be constrained in any way, and because the stinger is quite flexible in the transverse direction, right. So, in the transverse direction it is very flexible, right. So, because of that it offers very negligible resistance to the motion of the structure along other degrees of freedom. So, structure can move perpendicular to the stinger, and it can also occupy any slope that it wants to occupy, right, at that point. So, it does not offer much resistance in those degrees of freedom, right. So, that is how we can then ensure that the force is applied by the shaker only along the axis of the vibration of the shaker, right, at the point of attachment. So, also at the shaker end generally a collet chuck is provided. So, this collet chuck at the shaker end grips the stinger, right, and then at the structure end the stinger is connected to the force transducer mounted on the structure through a threaded connection. So, in the force transducer there will be a arrangement through which the stinger can be connected by a threaded connection. Another important point is the alignment of the stinger and shaker with the attachment point on the structure. So, what is meant by alignment? If the shaker vibration axis, right, the axis of vibration of the shaker is hypothetically extended in space, then it must pass through the point of attachment on the structure. When this is not realized, then what would happen? The shaker would not only apply the force along its axis of vibration, but it would also generate or apply forces in other directions. It may also apply some moment on the structure, right, because of this misalignment. So, this alignment of the stinger and shaker with the attachment point is very crucial. Otherwise, the FRF we measure will not be correct measurement, because for FRF measurement we need to apply force only along the direction of 1 degree of freedom, right. If the alignment is not proper, then the force will be applied in along multiple degrees of freedom, right, and then that would violate or will be inconsistent with the definition of the frequency response function. Now, the shaker when connected to the structure forms a complete coupled system, right. So, the shaker and structure together form a coupled system because they are physically connected through stinger. and therefore, the mechanical properties and electrical properties of the shaker system, they affect the dynamics of the coupled system, right. So, it is important to know that what is this interaction, how the dynamics of the shaker and structure interact, because then we would exactly know that what measurements we should take, so that we are able to measure the frequency response function on the structure, right. The frequency response function corresponding to the structure we measure, and not the frequency response function of the coupled system, right. That is what we want to know. Another thing is that the force that is generated by the shaker, right, it vibrates not only the structure, but also the shaker mechanical system, right. So, the force generated is shared by the structure and the shaker, okay, and therefore, the shaker properties also affect the way this force is shared by the shaker and structure. Therefore, by analysis of the interaction between the shaker and structure, we would like to figure out what measurements we need to take in order to identify the dynamic characteristics of the structure. Okay. So, what we are going to do is we are going to now take a lump parameter model of the shaker structure system, and then we will try to determine the FRFs between various inputs and outputs, and try to study them to see that what measurements or what particular FRF leads to the correct estimate of the dynamic characteristics of the structure. So, let us look at a shaker structure interaction model, and we are going to use a lump parameter model. So, we are going to take a single degree of freedom model each for the shaker and the structure. So, this is the lump parameter electromechanical model of the shaker structure. So, you can see at the top we have this structure model here, right. So, here the Ks, Ms and Cs are the stiffness, mass and viscous damping characteristics of the structure. Then we have this stringer here, which is connecting the structure with the shaker, and here we are assuming that this stringer is rigid, right. We are assuming this stringer to be rigid. So, it provides a rigid connection between the structure mass and the exciter mass. And of course, the degree of freedom here is this degree of freedom x, right, that is x. And then the shaker is now again modeled by a single degree of freedom system, and so this is the shaker model here you can see, and here the Ke, Me, Ce, they are the stiffness, mass and viscous damping coefficient of the shaker. Then we have the coil which is wound around the armature of the shaker, right. So, the coil is also shown here, this is the coil, and this coil is placed in a magnetic field as being shown by the poles N and S of the magnet. Okay. Now, this coil has its electrical properties which determine the current which flows to the coil. And so, therefore, the resistance and inductance of the coil are shown here. You can see this is the resistance of the coil and this is the inductance of the coil. Okay. And this coil therefore is being supplied the voltage by the power amplifier. So, the power amplifier has certain gain. So, let us say GV is the gain of the power amplifier. Okay. So, E is the output voltage of the power amplifier. The input to the power amplifier comes from the signal generator. So, V is the output of the signal generator. Now, we also see that this coil carries current, right, and it is placed in the magnetic field. So, what happens when the coil moves under the action of the force acting on the coil, then what happens, the coil cuts the magnetic lines of forces, and therefore, the magnetic field linked to the coil, right. The magnetic field associated with the coil that changes with time, right, and the Faraday's law says that if there is a change of magnetic field, right, with time, then it induces what is called as EMF in the coil. Okay. And Lenz's law says that the direction of this EMF that is induced is opposite to the direction of the voltage which is inducing current in the coil, right, and that is why we refer this EMF as a back EMF, because it opposes the voltage which is inducing current in the coil. And this back EMF, if we represent by EB, then its polarity will be then opposite to the the voltage E which is inducing current in the armature circuit. So, that is why we see in the figure that the polarity of EB is shown, which is the back EMF opposite to the polarity of E, right. So, this gives us a lump parameter electromechanical model of the shaker structure system. right. And now what we are going to do, we are going to write in the fundamental equations, okay, governing the working of this system, right, and then we will try to then determine the FRFs based on those equations. The power amplifier, it can be operated in voltage mode or current mode. So, the voltage mode of operation means that the output voltage of the output voltage E of the power amplifier is held constant, right, while the output current of the amplifier may vary as the excitation frequency varies. In the current mode of operation, the control system of the power amplifier ensures that the output current delivered by the power amplifier is constant, while the output voltage of the amplifier is adjusted depending upon the change in the frequency of the motion, right. So we are going to now focus our attention on the voltage mode of operation, and then we will write the governing equations of the shaker structure system based on that mode. So the first equation we can write down is the output of the power amplifier is proportional to the input voltage. So V is the input voltage to the power amplifier, E is the output voltage, and they are related by the gain of the power amplifier, which is GV, right. So this is the first equation. We also know that the back EMF which is generated in the coil is proportional to the velocity of the motion, right. So x dot is the velocity, and then Kb is the back EMF constant. So here Kb is the back EMF constant, right. So therefore Eb is proportional to the velocity, and it is equal to, therefore we can write down Eb is equal to Kb into x dot. So Kb is a constant of the system, and it depends on what is the magnetic field and what is the conductor length, right, or the length of the coil. Here Gv also we should note that it is the gain of the power amplifier, right. Then we can now we use the Kirchhoff's voltage law in order to write voltage drops, right, across the armature circuit. So E is the input voltage to the armature circuit, and then the voltage drop across the resistor is Ri, that is the voltage drop across the resistor. Voltage drop across the inductor is L into di by dt, and Eb is the back EMF. It is seen that the time constant of the electrical part of the shaker system is much lower than the time constant of the mechanical part of the shaker, right, and therefore this L into di by dt term can be neglected, okay, because the time constant of the mechanical system of the shaker determines the overall time constant of the system. So we can, for a simplified model, we can neglect the effect of inductance, okay. So with that assumption, we get the equation E is equal to Ri plus Eb. Then the force on the force generated on the coil is proportional to the current to the coil, right. That is why F is equal to Kf into I. And what is Kf? Kf is the force constant, of the coil, right. So it's a constant for a given coil. And now if this is the force generated, now we can write down the equation for the mechanical part of the shaker structure system. What is the effect of this force? And then we can use the Newton's law, right, to write that equation. So here you can see, because the shaker and the structure, they are connected by rigid stringer, so therefore both have the same displacement x, and therefore the force x on the mass ms plus me and produces acceleration x double dot. And what are the forces which resist this motion? They are the damping forces Cs plus Ce into x dot and Ks plus Ke into x. So basically the damping and the stiffness characteristics of the shaker and the structure system, they act in parallel, right, in this model. So this is the result of the application of the Newton's law. So these are the governing equations for the system, that electromechanical system. And now we can derive the FRF of interest using these equations, right. Let us first of all now look at the frequency response function x upon V, that is V is the input to the shaker structure system and x the displacement of the system as the mechanical displacement as the output, okay. So, we can obtain this equation by combining the equations we wrote on the previous slide, right. So, in this equation now we have got the voltage as the input appearing on the right hand side of the equation, right. Kf upon R into Gv is the constant, and then on the left hand side we can see we have additional damping term here, Kf into Kb upon R, right. So, we see that. So, this is the term appearing in the damping part, and therefore, it acts like a damping. So, this term is called electromagnetic damping. So, this is the equation we get, right. So, now if we assume the input voltage to be harmonic of certain frequency omega, then by solving this equation we can determine the ratio x of omega upon v of omega, right, because if the voltage is harmonic, the displacement, velocity and acceleration will also be harmonic, and then we can determine the ratio x of omega upon v of omega, and that ratio turns out to be this. So, this is the frequency response function between the x and v, and what we note from here. So, in the denominator of this equation we see that we have the stiffness, mass and damping characteristics of the coupled system which are appearing. So, based on the denominator we can say that the peak values or the peaks in this FRF, that is the frequencies at which this x upon v attains very high value, those frequencies will correspond to the natural frequencies of the coupled system, right. So, therefore, we see that the peaks in x of omega, they correspond to the natural frequency of the coupled electromechanical shaker structure system, right, because in the denominator the coupled system stiffness and mass properties and damping properties are appearing. So, this is a very important conclusion. This shows that if we measure the frequency response function in terms of x upon v, right, because v is basically like an input acting on the whole coupled system and x is the output. So, if you measure this FRF, then we will not be able to determine the dynamic characteristics or natural frequencies of the structure. What we would get by the analysis of this FRF would be the natural frequencies of the coupled system, right, because the peaks in this FRF correspond to the natural frequencies of the coupled system. Let us look at the FRF x upon Fs. What is Fs? Fs is the force shared by the structure, right. So, the total force F can be written as Fs plus Fe. Fs is the force shared by the structure and Fe is the force shared by the exciter or the shaker, okay. So, Fs is the force shared by the structure and Fe is the force shared by the shaker or exciter, right. And if Fs is the force acting on the structure, what would be the equation of motion of the structure? That can be obtained by applying Newton's law to the structure with force acting equal to Fs, and that would be simply ms x double dot plus cs x dot plus ks x is equal to Fs. And therefore, if the voltage input is harmonic, the force generated will also be harmonic, the force shared by the structure will also be harmonic, and in that case the displacement of the system would also be harmonic, and then we can easily work out that FRF x upon Fs as 1 upon ks minus ms omega square plus I omega cs. So, what we now observe here in the denominator of this FRF, what we see, the properties of the structure alone are appearing, right, and therefore, the peaks in this FRF or the frequencies at which this FRF attains very high value, peak values, they would correspond to the natural frequencies of the structure alone, right, and therefore, we say that the peaks in the x upon f correspond to the natural frequencies of the structure alone, and therefore, it would make sense to measure this particular FRF. So, if we measure this FRF, that is displacement divided by the force shared by the structure, or if we are measuring acceleration, then acceleration of the structure divided by the force shared by the structure. If this FRF we are able to estimate, then the analysis of this FRF would give us an estimate of the natural frequencies or the modal properties of the structure alone. So, this is I think another important conclusion which comes out or emerges from this analysis of the shaker structure system, right. Also let us study what is the FRF Fs upon V, means if V is the input voltage input to the shaker structure system and if Fs is the force shared by the shaker, what is the FRF Fs upon V. So, if you again use the equations we presented earlier, then this FRF expression comes out to be this, and what we note in this, we note that in the numerator we are having this term Ks minus Ms omega square I omega Cs, right. So, now this term, the numerator of this FRF becomes very small at the frequencies equal to the natural frequency of the structure. So, when omega becomes closer or equal to omega the natural frequency of the structure, then the magnitude of this numerator part will become very small, which basically means that the force which is shared by the structure at these frequencies would be very small, right. So, therefore, the values or the in the Fs upon x FRF or the frequencies at which the Fs upon V FRF magnitude is very small, that is the values in the FRF, they correspond to the structure's natural frequency, which means that the force acting on the structure becomes very small or the force shared by the structure becomes very small at the structure's natural frequencies, and this phenomena is referred as force dropout, correct. So, this therefore, what is the conclusion, that if there is a voltage input given to the shaker structure system and if the frequency of the voltage input is equal to the natural frequency of the structure, then at those frequencies the force shared by the structure will be very small, right, and this phenomena is referred as force dropout. And what is the reason for which this force shared by the structure drops to very low values at the frequencies of the structure, at the natural frequency of the structure? The reason is that if the structure is made to vibrate at its natural frequencies, then structure can vibrate naturally at those frequencies, right, because these are the natural frequencies of the structure, and therefore, the resistance offered by the structure to its motion is very small, okay, at those frequencies, and therefore, the structure does not require force, much force to vibrate at those frequencies, and that is why the share of the force it has in the total force becomes very small, right. So, structures can easily vibrate at those frequencies, and therefore, whatever force is generated, most of it then is used to accelerate or vibrate the mass of the shaker, right, and that is why the force dropout occurs when the frequency of excitation is equal to the natural frequency of the structure. So, this is another very important conclusion which emerges from this study, and then it is seen that because of the force dropout, the signal to noise ratio of the force signal becomes very small, right, it becomes poor at those frequencies, and therefore, that makes the FRF estimate of those frequencies to have larger error. So, let us now simulate a typical shaker structure system. So, we have now taken specific values for the parameters Ms, Ks, Cs and Me, Ke, Ce and other electrical parameters of the system, right. We have taken some specific values, typical values, and then we have tried to find these FRFs, right. And then we see that the undamped natural frequency of the combined shaker system for this particular simulation is 123 Hertz. Okay. So, the undamped natural frequency of the coupled system is 123 Hertz, while the natural frequency of the structure alone, right, 128.9 Hertz. Okay. This is something we want to determine. And now, if we determine the FRFs x upon V and x upon Fs, right, you can see they are shown here. These are the FRFs that are being determined, x upon V and x upon Fs, and then they are overlaid in this figure. So, what we see, the peak in the FRF x upon V, right. So, you can see this is the peak in the FRF x upon V. This peak is at 123 Hertz. Okay. So, the peak in the x upon V FRF it occurs at the natural frequency of the coupled system, while the peak in the x upon Fs FRF that occurs at the natural frequency of the structure, correct. So, this is clear evidence that the peak in the x upon Fs FRF is something which tells us the true natural frequency of the structure. So, this figure on the right, you can see here now we are overlaying the graphs of Fs upon V, right, and x upon Fs. Okay. So, x upon Fs basically gives us the true natural frequency, right, the peak in the x upon Fs FRS gives the true natural frequency, and then what we see that the graph of Fs upon V, it drops severely when the frequency is equal to the natural frequency. So, we can see this is the natural frequency of the structure, and at this frequency this force drops significantly. The force drops significantly at this frequency, which basically again is an evidence that force dropout does occur, right. The force drops when the frequency of excitation is equal to the natural frequency of the structure. So, now let us also now talk about how the force can be measured. So, often a piezoelectric force transducer is used to measure the force, right, which is applied by the shaker, right, and this piezoelectric transducer works on the principle that we have, if the piezoelectric crystal is subjected to a force, is applied a force, then it deforms, and the charge developed by the piezoelectric crystal is proportional to the deformation, and deformation is proportional to the force. So, therefore, the charge developed is proportional to the force that is applied on the crystal. So, this is a typical arrangement of a force transducer. So, this force transducer, let us say, will be attached to a structure like this. For example, we can have a structure like this which we want to excite, and then using some threaded connection or some suitable connection we can attach this like this, and then here we can have the stinger. Okay, this is the stinger. So, and then this stinger is going to apply force like this. So, what is going to happen? The force that is being applied, F, that would pass through these piezoelectric discs, right. So, these are piezoelectric discs. So, here in this particular example we have, there are two piezoelectric discs, right, and they are arranged such that the charge developed on each disc will be algebraically added. Okay. So, this is the ground terminal, this is the ground, the charge would develop on these surfaces, charge Q, right. So, when the force is applied, the two crystals undergo deformation, and then the charge is generated, and this charge is then collected, right, and this therefore, what we get here is a charge signal. Okay. So, again these transducers can be of ICP type or non-ICP type, and then if it is ICP type, then there will be an inbuilt integrated circuit which will amplify the charge and convert it to the voltage, and then we will get a voltage signal as the output of this transducer, right. And the sensitivity of this transducer, as we discussed earlier, will be in terms of if it is a charge type signal, then it will be in terms of picocoulomb per Newton, right, that will be the sensitivity, or if it is a ICP type or IEP type of force transducer, then it will be in terms of millivolts per Newton. So, this is how the force is measured. Another important thing is that because we want to measure the force shared by the structure, this placement of force transducer should be as close to the structure as possible. So, you can see here, that is why this is the structure, and the force transducer has been placed very close to it, right. It is not that it is placed on the shaker end of the system. If the force transducer is mounted at the shaker end, then it will not give a correct estimate of the force that is being applied on the structure, because there will be the stinger mass also in between the force transducer and the structure, and that will also share some amount of force, and hence the force that we measure will be the force that is transmitted to the structure plus the force that is shared by the stinger, right. So, that is why in order to get a correct estimate of the or correct measure of the force that is being applied on the structure, the force transducer should be placed as close to the structure as possible. Another requirement in model testing is the measurement of point FRF or driving point FRF, and driving point FRF means measurement of FRF with respect to the same excitation and response degrees of freedom, and for that therefore we need to measure the response where the force is being applied. So, it may be difficult to mount the accelerometer exactly where the force is being applied, and that is why we have something called impedance head. This impedance head allows measurement of point FRF. So, this impedance head combines an accelerometer and a force transducer into a single unit, and this is a typical schematic of an impedance head, right. So, you can see on the top we have this part is the accelerometer, and this part of the impedance head is the force transducer. Correct. So, you can see in the accelerometer part we have the seismic mass. So, we have studied earlier the piezoelectric accelerometer, and piezoelectric accelerometers have seismic mass, and then we have the piezoelectric disc, and then we get the output as the charge signal, which is proportional to the relative displacement of the seismic mass. And in the force transducer we have the output as the charge, which is proportional to the force that is acting on the piezoelectric disc. Okay. So, here because we want to place the force transducer closer to the structure, and that is why the force transducer will be attached to the structure through the driving surface. So, this is the driving surface, and through this surface we would attach the force, this impedance head, to the structure, while through the mounting surface we will apply the force, okay, and then that would be connected to the shaker part of the system. So, in this way today we looked at the excitation of a structure using a shaker, we looked at the typical experimental setup that is used for excitation, and also we looked at effects of interaction between the shaker and structure, right, and we also looked at force transducer and impedance head, which are used for model testing. Now we stop here. Thank you.